Why isn't it showing? Okay. Okay. And window. Okay. Okay. We should be set up. Okay. So any oh. Okay. Hopefully this is fine. Hello. 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 Wait. Why isn't this working? Hello. Hello. Okay. No, it's more. Taste. Microphone test. And this is weak right now. Hello. 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 Is this working? Hello. 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 Okay. I'll try to speak a little louder because leaking of power here. Okay, anyway, any question from last time? We were going through quantum Fourier transform last time, okay? So yeah, quantum Fourier transform is actually not an oracle algorithm. It's just an algorithm that do Fourier transform on quantum data. And so this is a generalization of discrete Fourier transform, which is something you do even in classical signal processing a lot. And the idea is kind of you transform between the so-called time domain and the frequency domain. So you are thinking your signal is the sum of a whole bunch of sinusoidals. And so if you have a lower frequency sinusoidal, then to frequency domain you have your signal in some lower frequency, and then you have higher frequency signal, and you have a spike in higher frequency. And if you have a superposition of those two, then you have like two spikes in those two, etc. Okay. So the idea is you can do Fourier transform and then inverse Fourier transform back in between the time and frequency domain, then kind of representing the same signal but in different perspective. But also, if you want to talk in more mathematical terms, it's just that you are viewing this vector in different bases, and you transform back and forth between two bases, different bases, by this Fourier transform matrix. Okay, so this Fourier transform matrix is a unitary matrix, and so you apply this unitary matrix, you can transform a vector to its Fourier transform. So this x vector Fourier transform to this y vector, and then you can apply inverse Fourier transform back from y vector to x vector. So it's like a change of basis, you apply unitary from, so you have a coordinate in one basis to coordinate to another basis, then you can inverse Fourier transform from one basis back to another basis. And so there is a small distinction here. So we were talking about this in classical. So we think about those vectors are classical signals. So you can just read that value. But then we go to quantum Fourier transform, and then it's the same thing. But now this vector, we think it as a quantum state. So it's a quantum state, and those numbers are the amplitude of your quantum vector. Okay. And yeah, so both of those are n-dimensional vector. And so quantum Fourier transform, then those are quantum vector, then there is a little more restriction. Because the quantum vector, they need to be normalized. So the norm square of those vectors are both 1. And so you need to check a little bit whether your Fourier transform, inverse Fourier transform preserve a non-UL vector, and that's actually true because they are unitary. So you can transform back and forth, and you will transform back and forth between two different quantum vectors. That kind of correspond to the Fourier transform of this quantum state. Okay, so that's quantum Fourier transform. And we have a few different ways to represent this transformation. So first we keep saying this is a vector and this is a matrix, unitary matrix, and we can write down the element of this unitary matrix is this 1 over square root n and omega sub n to the kj. So the kj's element is this thing, and omega sub n is the nth root of 1. Okay, so we are thinking root of 1 in complex plane. So it's e to the 2 pi divided by n. And so for example, you can think about complex plane is real axis and a complex basis. And if big N equal to 5, then you have this e to the 2 pi divided by 5 like this. So this angle is a whole circle divided by 5 here. And then you have omega n and omega n squared, omega n cubed, omega n fourth like this. And so so this Fn matrix depends on what's your n, and we have a few examples here. So you have some normalization factor in front, square root n, and then you have those omega listed here to some power, okay, to the kj power, where kj are x and y coordinate over this matrix. And you can have different representation. You can also, okay, so here we have two different things. So here we are writing yk, so the resulting, so the kth component of the resulting vector is the summation summation over j xj e to the 2 pi jk divided by n. So this can be seen as this matrix equation. So so y vector is some j f kj and f something j and xj, etc. Okay, and then we have also a different representation. Okay. Am I doing this wrong? Because it's okay. Yeah. And okay, so that's yk, and we can also think about yeah. Although I feel this is a little weird, but I guess we are not wrong. Okay, I will check this later. But anyway, so that's so that's yk. So that's like you say what's the case component here in terms of sum over this thing. And the other thing you can write is you can think about if you just have the j component here. So if you have a cylinder basis, so 0, 0, 1 is 1 is the j's component here, and what is the get mapping to. And the last thing is this formula. Okay, and yeah, so you can also get this from your matrix equation, and it's very similar to this yk thing, but anyway you are going to sum over different k. Okay, so if you just have a j a computational basis j vector inside, and you will get into everything. And it's so yeah, so basically you get a sinusoidal here, and it is sum over all possible k and e to the 2 pi jk divided by n. Okay, so and once again by linearity, then this is equivalent to you have defined all the quantum Fourier transform matrix. Okay, so if your transformation satisfies this thing, then it's quantum Fourier transform, because we have said what this transform do on all computational basis vector, and what does this transform to other vector is just by linearity, right? It's just by this thing, and yeah. Okay. Okay, and then we go to the thing that will actually connect to our topic today. Okay, and so this is the result we want to grade on quantum Fourier transform. And now we start going into a bit of phase quantum Fourier transform. So first we define this founding notation, which we will also use today. So we start to write numbers in bit string. Okay, so we usually begin to n, and we write numbers in bit string, and it's just basically writing number in binary. So say in decimal number 6 is 110, and we also write those fractional numbers in binary. Okay, so now this is less standard. Yeah, this is less standard as these things you see in CS, but I think this is pretty intuitively defined. Okay, so like 0.11 in binary is 3/4. Okay, and I guess this is a little confusing because we didn't specify which numbers are binary, which numbers are decimal, but hopefully from context it's not too confusing, and we also sometimes, I guess most of the time I will do underscore, but we haven't been trying to do underscore to distinguish between binary and decimal. Okay, so let's say we underscore 0.11 is binary, and then in decimal is 3/4, etc. And anyway, back to our quantum Fourier transform. So back to our quantum Fourier transform, we want to do this thing. And we find out that it has this nice factorization form. So if you want to transform a computational basis state, so this J now we write as bit string. So if it is J1, J2 to Jn, so every qubit is in 0 to 1, then the transform state is also a product state. And the transform state is like every qubit is a superposition between 0 and 1, but with this weird phase on 1. Okay? And this weird phase is e to a 2 pi 0.jn, and e to a 2 pi 0.jn minus 1 jn to all the way to 0.j1 j2 to jn. And so this is a number between number of the either 0 or 1 minus 2 depending on jn, and this is something from 0 to 3/4 depending on jn minus 1 jn, etc. So you get a higher and higher precision fraction here, and precision go from 1/2, 1/4, 1/8 all the way to 1/2 to n. Okay, and then we have this formula. Then we find out that you can do quantum Fourier transform with this kind of circuit. So you, I guess in this 3 qubit example, so you can do this kind of circuit. So you do hidden mark, control rotation, hidden mark, control rotation, and hidden mark. So you will rotate those qubits one by one into those those superposition between 0 and 1 that you want. And then we see the order is actually reversed than the input order. So and you need to do some swap gate to swap the order back. And we see that this is about order and square operations you need to do our quantum Fourier transform. And this is much faster than classical Fourier transform. Classical Fourier transform, if you do it a naive way, you need order and square. And the fastest possible is order n log n. Okay? And this is big N, so it's exponentially slower than our quantum Fourier transform log square n. Okay? But then we have a catch that the quantum Fourier transform doesn't actually do Fourier transform, because it Fourier transform a quantum state instead of classical data. Okay? And it's hard to get classical data back from quantum state. Okay? So what can quantum Fourier transform do? It's the thing that we actually talked about today. Well, I guess quantum Fourier transform can do a lot of things, but the biggest application here is to do this phase estimation. Okay? And yeah. Okay, yeah. And okay, yeah. And so for the phase estimation is actually a very quantum task you want to do. Okay, so it's asking that, so you have some unitary. Okay, say you are given some unitary u as a black box, and so unitary they have eigenvectors, and say u is 1 over u. So this small u vector is the eigenvector of this big U. Then you can write down eigenvalue equation, and you have this should be lambda u. But we say u is a unitary, then it means all the lambda should have known 1. Okay? So its eigenvalue must be some phase. So like this e to the 2 pi phi. Okay? And yeah. And well, in this e to the 2 pi phi, you see everything is this e 2 pi, they are all universal constant, and so only z depend on u is phi. Okay? So maybe use highlight. Okay, yeah. So it's phi. So this phi depends on your big U and also the which eigenvector you are selecting, obviously. But anyway, so now the quadrant is how you find this phi. Okay. this is a pretty quantum text you want to do. You have a quantum gate and some eigenvector of it, and you want to find the corresponding eigenvalue. Okay, so that's the phase estimation because, well, the eigenvalue is this whole thing e to the 2 pi phi, and well, it's a phase because it's known one, so that's called phase estimation. Yeah, and yeah, as we said, u is unknown, is given as a black box, and want to estimate this phi, and when you have some copy of u, okay, and yeah, that's a phase estimation test we want to do. And but actually the setup is a little different than what we described here. So if you just have those, it's pretty hard to do. Okay, so we actually want, instead of having u as black box, we want to have control u as black box. Okay, yeah. So we want control u as a black box, and actually if we want to do this very efficiently, we not only want control u, we want able to do control u to the 2 to the j. So we want to do a lot of u very fast. Okay, somehow. And we'll justify that we have this when we do factoring later. But for now, just assume we have those things. Okay, and okay. But anyway, so let's talk about have control u first. So if we have control u, how we do phase estimation? How do we estimate this phi to some precision? Let's first say I have a toy example. So we have this phi to lowest possible precision. So remember, phi is something between 0 and 1. Okay. So because phase is once again read our favorite complex plane, right? Phase is something on this circle, right? So that is a circle of unit 1 is e to the 2 pi phi, and then if your phase is this thing and phi is this thing. Okay, so phi, well, not quite this. Depends on. Phi is like the fraction of the whole circle you have, and so I guess this is 2 pi phi. Okay, so like here, then phi is 1/2, and yeah, so phi go from 0, 1/4, 1/2, 3/4, and 1, and 1 equal to 0. Okay, so that is phi, and want to estimate phi. Okay, so what's the lowest precision possible? That's phi either between 0 or 1.2. And so if you write in binary, it's like 1 bit of binary precision, right? Okay, so it's 0, 142 is 0.1 in binary, and 0 is 0.0 in binary. So it's 1 bit in binary. Okay, so yeah, so 1 bit binary precision is the lowest precision of phi want to get. And okay, so we promise that the phi is either between those two. It's very low resolution, and okay, so we want to determine those two cases. So if you write it out, it's either uu equal to u. That's when the phase is 0, so nothing happens. And when phase is 1/2, then your e to the 2 pi 1/2 is this point, that's -1. So u will be -u. And we're already seeing the circuit that can, well, not quite a circuit, but a very similar circuit that can do this. That's like the phase kickback circuit that we've been doing. Okay. So the circuit that distinguishes those two is this thing. Okay. And because yeah, this -1, where this +1 to the something thing is very similar to our first version of our code, right? And I guess it's easier to just analyze this circuit now here. Okay, so plus state and u here, and well, so this u is this eigenvector u here, and so you put plus state on the first register, and you control on this plus state. Then you either do your u on big, or I should write big U here. Sorry. So you either do big U here or you don't. Okay. So big U here, and and yeah, and then you see what's the output. Okay. And let's see what is happening. This is very similar to phase kickback, where we have phase kickback, we do like minus stay here, and we do our code. And we see that we also have phase kickback with this control U here, because what happened is the control U on plus and U, and okay, and the plus stay is 0 plus 1, and you have some normalization. Okay. And as we said, well, the control U, if the control qubit is 0, then it should do nothing, so this is 0 U. And if it's 1, then you actually apply U on the second on this state, right? So here you should get this U thing, okay? And well, UU. Then what's UU is you should have this e to the 2 by FIU. Okay? And yeah, this is by definition is eigenvalue is e to the 2 by FI. And okay, and now you see that the phase kickback happen because the second register is always going to stay as this small U state. Okay? So you can put the phase together with the first qubit and just write them together. And they are just tensoring the second qubit with this U. Okay. So yeah, so you got okay. Now we analyze what's this 0 plus e to the 2 by phi1 thing. And there are two possibilities because we say the phi is either equal to 0 or 1 over 2. So phi is 0, then obviously it's still 0 plus 1, then it's plus state. And if phi is 1 over 2, then it's 0 minus 1, and it's a minus state. Okay. So yeah, so you see the first qubit is either, so this e to the 2 by phase get kicked back to the first qubit, and that turns this into either a plus state or a minus state. And you can just do head map and measure this, and it will distinguish between plus and minus, and yeah. And that will do this very easy version of phase kickback. It will tell you whether phi equal to 1 over 2 or 0. If you promise that there phi is 1 over 2 or 0. Okay. Okay. Any questions on this toy example of phase kickback? Okay. And yeah, so a few things to note here is that, well, so I guess the first constraint we should have is that it only works for phi equal to 0.J1. So if I have this very zero position, they also need to be promised that is exactly in this form. And they also you need to have one copy of your eigenstate here. Okay. So there are quite a bit of a restriction on our phase estimation algorithm, and they will solve with these problems later. Okay, and okay, so I guess the first problem to solve is what if we have more bits? Okay, so if our phi is not 0.J1, okay, so we kind of want phi to be arbitrary, but now we do slightly smaller generalization, but this is anyway, yeah. So let's still have a restriction on phi. So let's say phi still have the bit string form. So it's still a binary bit string. So it's 0.J1, J2 to JT in binary. So it's a T-bit binary fraction, and so precision here is like 1 over 2 to the T. Right? Okay. So it's 1 over 2 to the T times some integer. That's phi. And okay, and there is something between 0 and 1. Okay, and now finally we can use our Fourier transform, because the thing we'll do is the circuit to do phase estimation is this. Okay, so you will have a T qubit here, and okay, so this makes a little bit sense because yeah, so you see you have when we have 1 bit precision, we have 1 bit to recall is 0.J1, And now with T bit, we want the TQ bit to record this J1 to JT. And yeah, so we have a TQ bit here, and what we do is we do hidden mod to length first. So now every one of them is 0 plus 1. And then we control on first Q bit to unitary. Okay, so this is kind of like we had before. Yeah. So this is, so if we just do this part, then it's like the 1 bit example we had. We will get 0.e to the 2 pi by 1 here, by the phase keep back. Okay, and but we also phase keep back on the qubit. So on the second qubit, we control on it, and we do u square. That's why we say we need to control u to the 2 to the some power. Okay, so if u square, then we still do phase keep back. So we can think about u square as another. So u square as another unitary, right? But so what's u square on u is will be e to the 2 pi phi square on u, right? And then that is e to the 2 pi 2 times phi. Okay, because you apply u twice, so you get twice over the phase. Okay, and yeah, so then we keep going. Then on the third qubit, we control it and apply u to the 2 to the 2, so basically u to the 4th. Okay, and so we keep this exponential up, and finally on the next qubit, excuse me. On the next qubit, we apply this u to the 2 to the t minus 1. Okay, and the next qubit will be this weird thing. Okay, and so now why we want to do this? Because this thing is now if you look at it closer, it's a little similar to what we had before for our Fourier transform representation. Okay, so this integral is actually so this from top to down. So this e to the 2 pi to the t minus 1 phi, e to the 2 pi to t to the minus phi, etc. And so now you think this phi is 0.j1, j2 to jt. Okay, and yeah, and this is the calculation we done before. So e to the 2 pi something, then we don't care about the integer bit. Okay, so this calculation we done before. So for example, 2 phi will equal to j1 dot j2 j3 jt, right? And this j1 we don't care about. Okay, and so 2 phi is effectively, if it's on the face, is j2 j3 to jt. Okay, etc. And so what's this? Okay, and yeah, so maybe let's look at it from back to front easier. So phi is actually obviously this 0.j1 to jt thing, because that's exactly what phi. And 2 phi we know is j2 to j.j2 to jt. So each time, so every qubit we go up, we multiply by 2, and then we lose 1 bit, and we push this fraction forward. Okay, so until the next one we get 0.jt, and the second next one we get 0.jt minus 1 jt. Okay, and so what's this thing? We have seen this before, and we have reviewed just a test. This is quantum Fourier transform of 2 to the t phi. The quantum Fourier transform of j1, j2 to jt. Okay, so this is this string. Yeah, and okay, so we see that if we do this kind of phase back, we get a quantum Fourier transform of j1, j2 to jt. And so now how do we get the j1? The information on j1 to jt is you apply the inverse of quantum Fourier transform. Then you will get this phi, which is j1, j2 to jt. Okay, j1, j2 to jt. Yeah. So yeah, so that's how you do phase estimation. It's basically a phase estimation circuit. Well, there are two parts. So basically, this is how you do phase kickback. Then you do inverse Fourier transform. Then you will get this J1 to JT. Okay, and so J1 to JT is like a 2 to the. Why do I get 2 to the? This should be 2 to the T phi. Can I erase this? No, it's different. Okay. 2 to the T phi. Okay. So that's the idea of quantum Fourier transform. Of phase estimation. So that's how you use quantum Fourier transform to do phase estimation. You do this 1 qubit by 1 qubit phase kickback. And then you see those product state has the same form of the product state of a quantum Fourier transform state. Then you apply inverse quantum Fourier transform, then you will get the actual state. Okay, and yeah, but I guess let's talk about this first. Okay, so we can have a little more abstract representation of this because we write down the whole circuit here is quite complicated. So we can make this a little more compacted. Then we say our phase estimation algorithm will look like this. I think this is also something that you can see on Wikipedia. So you have T bit of 0 here at start, and then you apply Hedema on all T bit. And now you think about all those things computational basis is like summation all possible computational basis state from 0 to the T minus 1. Okay, and then what you actually do is you do control U on K. Okay, so I guess this is a little bit of conversion here we need to check. So we are saying we are writing this bit by bit here, right? So we think these are the T bits. So the thing here are the T bit string here. So after Hedema, we have a T bit string here. So the first bit is the highest bit. So the T bit string convert to decimal is like 2 to the T minus 1 times the first bit, then 2 to the T minus 2 times the second bit, So like 1 times the last bit, and 2 times the second bit, and 4 times the third bit, etc. Right? So that's why you have a U to the 1, U to the 2, and a U to the 4. Okay. So you see the total number you do is actually just same as the computational basis state here as a bit string. Right? So yeah. So once again, J1. I guess it's not. Yeah. So like I say you have only 3 here. So you have one. Sorry. Let's go back to stuck here. Yeah. So let's say if we only have 3 things and we have a 1, 1, 0 here, and the bit string corresponding to 6, and the number you do will be 6 because it's 4 plus 2 plus 0. Okay. Yeah. And so this thing, what they actually do is, so you apply Hedema to it, and you can think about this computational base that as some k from 0 to the T minus 1, and then you do this super control U, where you apply U to the case power. Okay, so I guess we never talk about this kind of control, but this control means that you apply, so you have T bits here, so you apply U to the case power depending on what computational basis that you have here. So the larger number here, you apply more U here. Okay, so this is what we do in the weird control in the middle part. Okay, and this U to the K will do a very strong phase kickback, and you do inverse QFT, then you measure here, and you should get 2 to the T phi. Okay, and yeah, because you can check that U to the K U is e to the 2 pi phi to the k's power U. and so stay here after you apply all this. Then the U part is still U, so you can just phase key back everything to the first qubit. And so here you just get this E. So sum over all possible k from 0 to 2 to the t minus 1, and e to the 2 pi phi k, and k tensor U. Okay. And we see this sum k e to the 2 pi phi k is very much like a Fourier transform state, and if you inverse Fourier transform, then we will get and yeah, because we compare to Fourier transform state, so computational based state Fourier transform will become e to the 2 pi I jk over n. So you see the same sum k like this here. And so everything, your big N is 2 to the t, and if our phi is j over big N, then this is exactly a Fourier transform state, and we can inverse Fourier transform back to get j, which is big N times phi, which is 2 to the n times phi. Sorry, 2 to the t times phi. Okay, and yeah. Okay, so yeah, so there are still two caveats here. So first thing is, well, your phi need to have this exact form, and so phi need to be equal to this sum j divided by 2 to the t, goes on into an integer j. Okay, and yeah, and later we will, I guess we will skip that, but the later part of this PDF has some detailed calculation to show that if your phi is not exactly a binary fraction, then actually you can still run this circuit to get a pretty good estimation of phi. You just need to run a little more bit of this. Okay. And the other thing we don't know is, okay, so how do we get this U? Yeah, because how you get the eigenstate, it seems pretty hard to always get the eigenstate. Yeah. And yeah, so but we have something nice. So if we don't exactly have eigenstate, then yeah, because things like, so if you just get some black box U, things like it's pretty hard to find the eigenstate also. And that's true, it's hard to find eigenstate. But even if you don't have eigenstate, then you can get something, and this is what we will do when we do factoring. Okay. So if you don't have eigenstate, and you can still put just whatever state here. Okay, just put whatever state here, and you can still face the estimation something out. Kind of ignoring the precision issue. So assume all the. So for now, assume like every eigenvalue of this U is in B string. Okay. Okay. So if you don't have eigenstate, and well, but the eigenstate is a complete basis for your whole space. So you can just write your whatever state phi as a superposition of eigenstates. Okay. And so what will happen is that, okay, so you run your phase estimation algorithm, you start with this 0 to a t. So this is 0 to a t. 0 to a t and phi. So maybe let's write 0 tensor t here. Okay. Actually, we don't care about precision, so whatever. So the 0 is actually a very long 0. Okay. So you run the 0 phi and you do phase estimation. And you can just see that by linearity. So yeah, so 0u should go to phi sub u, right? Where phi sub u is the phase of correspond to this u. Okay, so 0u should go to phi sub u, and then is 0 and the superposition of a different u should just go to superposition of a different phi and u, phi sub u and u. Okay. This is just the linearity of quantum algorithm, because phase estimation is a linear transform. Okay. Phase estimation is doing exactly this. Okay. So we're basically saying what is the state at this step. So just before your measurement. Okay. And because everything is the unitary, which is linear. So if you have a linear superposition of a different input state, then you get a corresponding output state linear superposition of a corresponding linear superposition of the corresponding output state. Okay. So yeah, 0u go to psi u psi sub u, then zero some coefficient u should go to some coefficient u and psi u. Okay. And okay, so I spent a lot of time saying you get this. But anyway, so what you can do here is now if you now you still measure this register, measure this psi u register, then you will actually get. That makes sense. Yeah, that makes sense. Yeah. Yeah. Now you measure the psi u register, then you will get your psi u with probability cu squared. Okay. Yeah. And so this tells us that even if you don't have eigenstate, then you can still get some information about the sum of the eigenvalue of your big U. So if you pick a random state, it has some superposition to different eigenvalues, different eigenvectors, then you will probabilistically get some of the eigenvalue. Okay. And yeah, so this might seems not very useful, but turns out it will be useful when we do factoring. Yeah. Okay. So it's kind of funny, but yeah, actually when we do factoring, we find out so obviously this psi u depends on which u actually hit with your kind of a random starting state, but we'll see that we'll pick a quite smart starting state, and almost every psi u get here will give us useful information when we do factoring. And I have less than 10 minutes, so I guess that's okay. Actually, any questions so far? So no, these are more important part because accuracy is a very annoying calculation, and I think this year was shorter, so I will just skim over it very roughly. I just talk about a high-level idea, and you guys can read the detail if you want. But phase keyback idea is very important, you should remember. So we are doing this U many times and the phase keyback. Oh, I guess one thing I forgot to say is, okay, so this thing. Okay, so you have this control U to the 2 to the J. So the 2 to the J part, this is quite important to have efficient circuit, right? Because so this K is possibly to 2 to the T. Okay. So if you just do this control U to the K with usual with control U, then you need to do like 2 to the T times 2 to the T. You need to have 2 to the T control U here, and that's very expensive. But if you have control U to the U of 2 to the J, then you only need a T. Okay. So if you have this thing, then you only need a T control gate here instead of a 2 to the T. Okay. So that's a lot of efficiency difference. Okay. So see here, you only have a T of those control here. Excuse me. So what I want to say is, you don't have this gate, then you need to actually use a 2 to the T control U here, and that's just too expensive. Because it's actually 2 to the T minus 1, but similar order. Okay. And okay, let's try to have 5 minutes talk about accuracy. I guess let's talk about the result. So the result of accuracy is, okay, so here we say that if our J is a T-bit string, then we can use a T qubit to get our J. And what if it's not exactly a TP string? Actually, we write n bit here. And if it's not exactly a TP string, then we can just use a little more bit. Okay, so let's say we want the n bit accuracy here. And then the number of bit t you use here is a little more. So depends on error. Okay. So now we need to introduce the idea of error. And so now your phase estimation algorithm will sometimes fail, and the fail probability is epsilon. And so you want epsilon, you need to add extra log 1 epsilon bits. Okay. That's the high level idea. And that's a little different from this thing because let's see here, this is everything exact, right? So this thing cannot fail. This thing will work with 100% probability if your phi is actually a bit string. Okay. And but phi is not a bit string, then we have some fail probability. Okay. So we see phi is okay. So phi is maybe even an irrational number. So you have infinite number of bits in a bit string. Okay. And so we'll estimate the first n bit of phi, first small n bit of phi correctly. And actually we use t bit. Okay. And so there are a lot of things we'll talk about. So I guess let's go here. So what do we say is it's very I don't think we can say in 5 minutes this. Okay. Yeah, so we'll differentiate this phi to a lot of different parts. So so there are this totally error part, and so there are function bits you want to get, and there is a difference between n and t, we call it p, etc. And what we will get is don't have time. Okay, and I guess we can talk about analysis a little bit, and maybe we'll resume this a little more next time. Okay, so the analysis is like you do 2 t bits. So you still run the same phase estimation algorithm as before. So you get those t bits precision. So you can think about your estimation result is something from 0 to 1, right? And you have a t bit precision, so you have those block here where, so like each of the block range is 1 over 2 to a t. Okay. And okay. And then you have your phi that's somewhere between 2 blocks here. Okay. And and we are now allowing some precision E here. So the precision E will be like a 2 to a P. Okay. So we have a P equal to. So we want the first n bits, and we have a P equal to n minus P equal to t minus n. Okay. P equal to t minus n. And when we do calculation, then we have we'll have an error. Error is like a 2 to the p. Okay. So error is like so you want to estimate your So you want to estimate like a b here. That's the so b is like is a phi, the first t bit of phi. So where this phi actually fall into. So I should signal this phi. Okay, this is more complicated than it should be. So this is a thing we want to estimate, but we cannot. Well, so there are multiple results. So basically, if it's possible, the best possible thing, then we want to find the basic estimation of phi in terms of those t-bit precision. And it's hard to bound that exactly to total precision. So what we do is we allow more accuracy of error here. So we allow like a E block here. Okay? So E is like 2 to the t minus n. And then we are saying if so we bound the probability of getting very bad result. So if you are getting some, So when we measure, we'll get 1 over the tick here. Yeah. And we are saying the probability going to very far away tick is very low. Okay. So we are saying the tail here, so each tick probability go like 1 over L square, where L is just whatever distance here, so L here. So L is kind of like E. And so the whole area of those tail will go like 1 over L. And if you choose L equal to E, and so we have a lot of calculation, and we will say the area goes like 1 over E. Okay. And yeah, so finally then we say, well, E is 2 to the T minus N, and you want this 1 over E to be epsilon. Then, okay. Yeah, so so you want this 1 over E to like epsilon, then the end result is you want your T minus N to be like log 1 over epsilon. Okay. So this is a very rough estimation. And so you are all over time, but actually there is another estimation that gives kind of a better result. So if you don't need epsilon area, you just want a constant success probability. Then actually there is another estimation says that, okay, so still the same thing, right? So you have a T bit, and so you have this 1 over 2 to the T precision. So we actually say this, you can actually also bound that this 1 over 2 to the T precision has a very high probability to get correct. So say your phi is here, right? So your phi is here, and so probability to get the base estimation, which is so if the peak is slightly to B plus 1 is here, and the peak is here. So the probability to get base estimation is actually at least 40%. So yeah, so this is some other estimation than this 1 very strong log 1 very strong estimation. Yeah, so sorry for overtime, but anyway, yes, at a high level, we want to say the precision of phase estimation is okay. Just need to do a little more bit, or accept with accepting a constant error probability. Okay. So yeah, so see you on Thursday.